Well, good afternoon, everybody. Thank you very much for giving me the opportunity to present the StarCore vision for the HTGR technology. I've titled our talk HTGR Technology Resilient, Reliable, and Ready. That ties in with the name of the symposium here, but we truly believe that is the case. My background, start off, I'm the leading up the systems engineering effort within StarCore. My background is mechanical and nuclear engineering. And to date myself, in 1979, I was a junior. And instead of becoming fearful of nuclear power with TMI, I kind of dove in with both feet and blind ambition. Took all the courses I could at Virginia Tech, and 2 years later, when I had a master's in mechanical, I also had 2 years as a senior reactor operator on their research reactor. So I became very pro-nuclear very early on. And after I left Virginia Tech, went out to industry, got bored, and went back to Stanford for my doctorate. Something about the water in California turns you into an entrepreneur pretty quickly, and that's where I became a power plant designer. I teamed up with a couple of other friends at Stanford, and we wrote a code called Gate Cycle, which is a heat balance code which is used to design power plants and do performance analysis. So my talk's going to be very different than the talks that you've heard from my two predecessors on the panel. It's going to be sort of laser focused on how an entrepreneur approaches solving the problems of our customers to get a plant in the ground as quickly and safely as possible and economically as possible. The agenda for the talk is to start out with an overview of StarCore's design, give you a little bit of the vision, and then I'm going to walk you through an example industrial application. This is actually based on a proposal that we put forward for a mining site. And it makes use of the combined heat and power capability of our plant. We had to address multiple operating scenarios for the client. And the client was in a very remote off-grid location. But that's the total focus of our technology. We are solely looking at locations that are off-grid. So we're not trying to compete with $3 a million BTU natural gas, because we'll never compete. But we recognize that there are hundreds of thousands and literally millions of people around the world that don't have access to clean water, low-cost electricity, and information. And so we can do a great service to those people by providing long-term clean electricity and desalinated water or clean water and information. So very briefly to go over our technology, we are trying to keep our vision very simple and safe. So a little bit of a tweak on the KISS principle here. We like to think of it as keep it simple and safe. Our HTGR is helium-cooled TRISO fuel and prismatic block. So we're really focusing on removing the risk. We want to get something built and licensed in the other order, licensed and built in a timely manner. And the way to do that is by reducing the risk. So what we're basing our blocks on is the proven technology. Fort St. Vrain has a lot of data, and we're using the prismatic block technology there. We're leveraging the wonderful work that's been done at INL. If you haven't been on that tour that I went on yesterday, I would encourage everybody to go on it. It's amazing seeing what they can do here. But we want to leverage all of the wonderful work that Hans and David Petty have done with the TRISO fuel. We're making use of that. And we have a bit of a different approach to the use of the heat. Instead of a steam cycle, we're using a Brayton cycle. And so we're taking the helium loop, the primary helium loop, we're taking that into a heat exchanger, which is then heating nitrogen in a nitrogen loop. So we've got the primary fission product boundary at the TRISO fuel. Then we've got a boundary within our primary pressure boundary for the helium. Now we've got another boundary with the nitrogen loop. And then the nitrogen heat is exchanging with an air-breathing gas turbine. What that does is it keeps a very simple system. We're trading off a bit of efficiency for flexibility and simplicity. This gas turbine, simple cycle gas turbine, is the workhorse for power generation in the US and globally today. Natural gas-fired gas turbines have been built at an incredible rate starting in the 1980s. And we believe that using this approach will give us the ability to build something more quickly, because the gas turbine is an air-breathing gas turbine, so I don't have to rely on helium turbines, things that aren't proven. As you'll see in a minute, our plant is not a very large plant. It's a 10 megawatt plant, and a 10 megawatt gas turbine is tiny. Anybody that flew in a wide-body jet today or coming to this conference looked at 2 gas turbines on the wings or 4 gas turbines on the wings, each of which were probably 50 megawatt equivalent gas turbines. So 10 megawatts is not large. The overall design for the plant is one where we anticipate putting the primary, the pressure vessel, reactor pressure vessel, in a silo. The silo, we believe, will be easy to construct in a remote location. So because we're focused on remote locations, we have to be very careful to design something that can be transported to the remote location and constructed easily at the remote location. And that presents many challenges. So we think the underground RPV silos are fairly straightforward to construct. We're going to precast the concrete. We're going to pre-construct as much of this in a controlled environment as we can. So we heard Finnis this morning very correctly identify the cost of construction, the time of construction as very important aspects to success. We believe that we can construct more quickly by having things precast and pre-built in a controlled manner. That will also keep the cost down, because we don't have the luxury of bringing in a large labor force to a remote location. So we need this to be as ready to go as we can when it gets to the site. Part of the reason for the small system is that when you're in a remote location, you don't need 500 megawatts. You need tens of megawatts, or tens of megawatts coupled together. We can couple a number of these together to get 100 megawatts, which is fine for a remote community. We're using high-strength concrete, modular construction, precast panels for our main containment, our main building here. We have a very unique advanced control system, a state-based control system that's used in the space industry. We anticipate that will take some time to get through the regulatory process. So we'll have a regular control system in concert with this, but then as the regulators see, as we demonstrate the benefits of the more advanced control system, we plan to transition over. The system will have high-speed data access. We've got multiply redundant data links going into the plant, so we can remotely monitor the plant and we can remotely shut down the plant. We're not planning on remotely controlling the plant. We will have operators, but we can remotely monitor and shut down. And because we're in a remote location, it's critical that we can load follow. The gas turbines are the classic way that we load follow around the world today for power generation. The approach we used in the architectural design was to create a power plant that the local community would adopt and be proud of. We didn't want an eyesore, and our CEO, David Dabney, is a sailor. And it's no coincidence that when you look at the shape of our plant, it looks like an inverted sailboat. So I'm not sure what that says about his sailing skills. Maybe that he was able to capsize a sailboat quite frequently, but it is a really aesthetically pleasing design, and we're quite proud of it. David Poole, the Chief Technology Officer and co-founder of the company, is an expert in this advanced control system, the state-based control system. So I'm going to go through the types of systems that we have very briefly, and then I'm going to walk you through a customized industrial design that we proposed for a mining opportunity. The simple cycle gas turbine is the most flexible and quickest load following solution for power plants today. We can ramp up very quickly up to the full 10 megawatts. The exhaust heat from that gas turbine can be used to generate steam, turn a steam turbine, and generate another 4 megawatts of electricity. So a single core, about a 35, 37 megawatt thermal core, will generate 14 megawatts electric. If we don't want to use that exhaust heat for electricity, we can create a combined heat and power system, and and we can arbitrarily swap back and forth between electricity and thermal process heat. So you've got a 37 megawatt core, you turn 10 megawatts into electricity, you've got 25 megawatts of heat going out the exhaust. You can use that for a multitude of purposes. One of those purposes would be to desalinate water. We can either do that through multi-stage flash if you're in a location that allows that, or we could have the combined cycle system generating 14 megawatts electric, use an RO-based system that'll get us about 60,000 cubic meters a day. That's 60 million liters a day. That's a fair bit of clean water for a remote location. The last approach that we can use is to customize our system around an industrial site. And that's what I'm going to spend the rest of the talk discussing. This particular opportunity was a remote mining site. And it was pretty typical of what we find. There are many mines around the world. And it's a great opportunity for our approach because they're generally very remote. They need load following. And they're long-term opportunities. So these guys are going to be in place 25 years typically. So it's a good mate with our technology. In this particular plant, they were using sulfuric acid for a high-pressure acid leach. And they made their own sulfuric acid on site. So the sulfuric acid plant was oxidizing. They were taking elemental sulfur and burning it to create sulfuric acid. That process is very exothermic and produces steam. And what I'm going through now is what the customer presented to us. This was their initial design. And we proposed a way to improve that design and replace all of the fossil-based systems with nuclear electricity and heat, nuclear-based electricity and heat. So in addition to the sulfur acid plant, they had two natural gas-fired boilers that were needed to produce additional HP steam. They needed about over 200 tons an hour of steam for the overall plant. They also needed a natural gas-fired gas turbine to produce electricity. And then part of the HP steam was consumed by this high-pressure acid leach, and electricity was required for the plant on the order of 43 megawatts electric. Steam turbine was used to generate part of that power. It consumed some HP steam. Sulfur melting consumed medium pressure steam, and process flows and deaeration consumed low pressure steam. When you're trying to satisfy a client needs, you can't just go and give them a single solution. You need to be able to satisfy all of the needs of the customer. And this particular customer had 4 major operating scenarios that they had presented to us. One was a design basis, which is the largest power and steam flow requirements. Second was sort of their normal operations, which was backed off about 10% on the power and steam needs. And then the last two operating scenarios were abnormal situations where if you had the fossil boilers go down, you would only have the steam from the sulfur plant. And if you had the sulfur plant go down, you would only have the steam from the fossil boilers. So we did a full engineering analysis of all of these. I'm not going to go through the numbers, just want to point out here that they give you a lot of information, and you have to understand that information and then present back a solution that matches exactly what they're looking for. So here's an overall heat balance diagram that we pulled together using gate cycle. And the first thing we needed to do was just model their plant. So we modeled their plant with the sulfur acid plant down here. We've got their fossil boilers up here. We've got their natural gas-fired gas turbine here. And so you're generating HP steam. It's going down to the process uses and the steam turbine, and then the steam turbine condenses the steam in the condensers through deaeration and then back. So you've got a big water loop. So once we were convinced we understood their plant very well, we took our technology and showed how we could dovetail our technology into their overall process needs. I'll show you more details of the different steam flows in a minute and our solution, but graphically here we've got our gas turbines. We have a 2-reactor solution here, so we've got 2 gas turbines, and we use the process heat from the exhaust heat from our gas turbine to create steam, and we also supplied steam turbines. So we were acting as an electricity provider and also a steam provider over the fence. So we were offering to sell them electricity and sell them steam for a protracted period of time to make it more of an apples to apples comparison for them. We recognized in looking at the design that they had, it really wasn't optimized very well. And so for some of those low pressure, medium pressure, and low pressure steams, they were de-superheating high pressure steam and throwing away a bunch of availability, which is stupid. And so we split our HP steam into superheated and saturated steam so that we would have better efficiency on our steam cycle. But the big picture here is that we had two plants. We're creating steam. We're also, in some situations, pulling steam back over the fence to us for our steam turbines to generate electricity. And then we ran this scenario through the paces and optimized to get the best bang for the buck and to show that we could meet all of their expectations and needs. When you look at the StarCore plant, here we've got the gas turbine. We've got the nitrogen, hot nitrogen coming in here. It's coming in, I should have stated, in order to minimize risk, we're not trying to press the edge of the envelope in any of our design criteria. So we're looking at core exit temperatures of 850 C, which allows more reasonable materials. We come from the helium at 850, we go into the nitrogen loop and drop about 50 C conservatively, which brings it down to 800. And then the 800 C nitrogen comes into this heat exchanger, which takes the place of the combustor in the gas turbine, and our compressed air out of the compressor is heated to about 750 C. So this isn't a state-of-the-art gas turbine, but it will be extremely reliable and robust. It's not going to have the efficiencies you're going to have of the 2400 degree firing temperature gas turbines, but we don't need that. We are looking for a reliable system. We're willing to trade off efficiency and flexibility for, we're trading off the efficiency for reliability. The exhaust comes through a traditional heat recovery steam generator. We've got a two-pressure system here, LP steam for deaeration and process steam, HP drum, HP superheater, and economizer to create saturated. We pull the saturated steam off, send that over the fence. We pull the superheated steam off, goes through our steam turbine, and it can go over the fence as well. And we can also import steam and put it through our steam turbine. So each of the two plants have the capability here of generating about 20 megawatts of electricity from the steam turbine and another 10 megawatts of electricity from the gas turbine. We also, because we have 800 C nitrogen, we can run that through a heat exchanger for the exhaust heat and superheat that exhaust air. That's called a duct burner in a traditional heat recovery steam generator. So we can duct burn, effectively duct burn to create more steam. You do that if you want to create more steam because that gives us another knob to turn, if you will. We can now turn down the gas turbine and turn up the steam turbine. So there may be times when you want to move things back and forth. So to summarize, I just want to say that these HTGR plants seem to be very well suited for combined heat and power opportunities such as this when you couple the process heat to a Brayton cycle. These types of mining operations are quite common, and they made up very well with our prime directive of bringing power and electricity, or power and process heat and clean water to remote locations. In this particular example, a 2-reactor plant was able to meet all of the needs of the regular design point and regular operating scenarios. And one of the alternative scenarios, we actually generally had to turn down the reactor because we had too much power. The one where the sulfuric acid plant was offline would require a little bit of supplemental steam from some other source. Most likely a smaller oil-fired fossil boiler would be required, but that's an extremely rare situation that would be a short term because if you don't have the sulfuric acid, you can't do the high-pressure acid leach and you can't run your process. And lastly, just want to point out that it's really the flexibility and redundancy that come from that combined heat and power configuration that gave us the opportunity to meet all the needs of the client. So I'd be happy to take questions. Funny.
comment. Your talk triggered me to remember something that I had from my Florida Power Light days. Key West never wanted to join a major power grid. They found them, it'd be onerous to deal with a large utility. So Key West has always had a municipal power, 2 diesels, 10 megawatts, provides all the electricity and the potable water because they do it with RO off that same electricity. So I'm going, gee, it seems like, no matter how you cut it, 2 diesels, it's $20 a million BTU for diesel. So, a nice, reliable, long-term fuel supply, 10 megawatt reactor would be a lot better, it seemed to me. So.
Oh, absolutely. One thing I meant to mention, and I apologize in the very beginning, we're a Canadian corporation, and we are planning on going through. We're in the process of starting the VDR vendor design review process for licensing, and we specifically have identified a number of locations that, mining opportunities, but also opportunities like you just mentioned, where you've got oil-fired systems. They're trucking the oil out, and those people can be spending 50, 75 cents, $1 a kilowatt hour. It's very different than what we're used to paying, right? So it's sort of like the old adage, you don't have to be faster than the bear, you just have to be faster than the guy next to you who's trying to run away from the bear. We don't have to try and meet 5 cents a kilowatt hour electricity rates. We just need to be able to improve on the electricity rates for the clients as they currently exist. And so these remote locations are very well suited for our company to be able to be the star and save them money, but we can at the same time generate a reasonable return for our investors who have invested in the plant and give them a reasonable return on the investment. I should also point out, in addition to remote locations, within countries like Canada, and Canada is an obvious choice for our licensing because of the access to remote locations and because of the favorable nature of the licensing process. Island locations are another good opportunity, where they have to either truck in liquid fuel or bring in LNG at fair expense.
Very good. Thank you, Leo.